So our final speaker today is Dr. Matt Oehlschlaeger, professor of mechanical and aerospace engineering. And Matt's also a member of my provost team. He is the interim vice provost of undergrad education. His research illustrates how artificial intelligence can be implemented to identify complex patterns in chemical and medical data, for example. His work enables a more sensitive selection and automated approach to chemical sensing and medical diagnosis. So think about imaging and diagnose from specific medical imaging. His talk today is entitled Decoding Fingerprints with AI, from chemical detection to medical diagnosis. He will share how artificial intelligence can be used to uncover patterns, signatures, and even fingerprints in complex data. Please join me in welcoming my colleague, Matt Oehlschlaeger.
Welcome back, everyone. It's great to see so many of you back here on campus to visit with us. How many of you are engineers? Yeah, I'm an engineer too. I like to make things. I like to make things that measure things specifically, so I'm an experimentalist. And so my experiment with AI has been, over the last 6 years, trying to integrate AI into other kind of measurement systems that we have that are well developed in order to improve those. And so I'm gonna present a couple of those today to you. So first off, let's just kind of wrap our head around the idea of a fingerprint. We all have fingerprints. They're unique. They're two-dimensional patterns in a grayscale, right, from black to white. And they identify an individual. So we all have an individual fingerprint. However, if I were to give you a fingerprint, you wouldn't know who it is, right? You'd have to go comb through a whole bunch of databases and try to determine, this fingerprint belongs to this individual. All right, so let's get the idea of fingerprints are everywhere. Patterns are everywhere, both in the man-made world and in the natural world. Here's another example. This is Vincent van Gogh's Starry Night. There are distinct brush patterns, distinct colorings that identify nearly every artist by a fingerprint style. Each of our voices, if you talk to a person for 30 minutes, you'll probably be able to recognize their voice for a long period of time. Each of our voices has a very strong fingerprint. We'll play.
We the people, in order to form a more perfect union.
So whose voice is that? Right, you know it probably within the first 3 words, we the people.
We the people.
How do I get to the next slide now? There we go. So what are you doing in these cases? You're sensing something with your eyes, your ears. You're identifying then features. You're not looking at the specific pixelation in that fingerprint, but you're looking for some kind of curvature or something. Within the voice, you're looking at the rise and fall of the sounds, the spacing of the sounds, the rhythm, and the words. You're then identifying features within those data sets, comparing them against your memory banks, and then classifying the painter, the fingerprint, the speaker. So let's focus in a little bit on that voice example. So your ear hears a signal, or hears intensity, and that intensity varies as time, and it also varies with frequency, right? It has some frequency content. So that's the signal you hear. Although I don't think that way about the voices I hear or the music I hear. Instead, I hear a pitch. What is the tone of the sound? What is the intonation? What is the rise and fall of the sound? Those are physical features that have to do with the time, frequency, content of the person speaking. I then hear phonetic or linguistic features, like the way they pronounce a word, the way they rhythmically speak. Maybe you might call those accents in some cases. And then also there are cognitive or semantic features, the words, the content, the meaning of what they say. So these go from microscopic to macroscopic, physical, phonetic, and cognitive. Those things together are then referenced against my memory bank, and I say, that must be the speaker, it must be Barack Obama. So we're limited as human beings because we have limited memory. We also have limited ability to form features. So one of the great things about AI is it has effectively infinite data capacity. We can train AI on pretty much anything that we can come up with. So we can increase its memory banks. AI has resolution to identify features that are far superior to many other modes of feature identification, including those that we have. For example, if you're listening to music and you don't have perfect pitch like myself, you can probably hear the difference between an A and a D note. One's higher, one's lower. But AI can tell you specifically, that's an A and that's a D. It has perfect pitch. It has resolution, and it's also quantitative. Therefore, it can be more objective than other forms of classification. It doesn't get tired. It doesn't need coffee. It doesn't need sleep. It's consistent. It can also be adaptable. Our training has taken place over decades. AI can be trained in seconds. And so we can adapt these models very, very quickly to do better. So I want to talk about two applications that are very engineering-centric that I've worked on. The first one has actually been something I've worked on for about 20 years. Air pollution is still a big problem in the world. And today we have super emitters that tend to be in large population centers. Here you'll see a map of nitrogen dioxide emissions from satellite image between Washington, D.C. and New York. Basically, we're all breathing terrible things. Pollutant compounds, volatile organic compounds that have unknown health effects. So what we would like to do is we would like to make it common knowledge what the air conditions are in this room, what the air conditions are outside, so that people can make judgments about whether they should be in those spaces. And so what we need is real-time chemical sensing. And so this is something I've worked on for quite some time. Chemical species in the gas phase can be easily identified by their fingerprint spectra. And they have fingerprint spectra because all molecules have quantized energy levels, and the transition between those quantized energy levels are unique to the molecules. If you have taken any physics classes, you'll notice that these are probably rotational and vibrational transitions in the energy levels of molecules. And so, for example, this molecule methanol has a very specific spectra. So traditionally, we would feed something like that into a hardwired code or give it to a chemist, and that person, through their expertise, would say, you've observed methanol. So I want to say now we can at least use AI to observe a single species like methanol quite easily. So we'll feed that through some pre-trained algorithm, and we'll use this AI to identify this single molecule methanol. Actually, really not that interesting of a problem. We should be able to use lots of methods to identify one thing. However, let's say we have something that's very complex, where I have lots of unknown information, like thousands of speakers perhaps speaking at one time, and I want to separate out those speakers. I want to then pass that frequency content through some kind of artificial intelligence system, and I want to separate it. And so we've demonstrated that we can separate dozens of molecules. Basically, we can separate any molecule that we can observe as long as we know in advance through physics what the spectra will look like. We can do this with extreme accuracy, like 99+%, near 100% accuracy. And so in the past, where we would zoom in because we were limited by human and hard-coded algorithms on single features within spectra, we can now take lots of frequency content, process it automatically through AI, and learn a lot more than we were in the past. So we're able to sense molecules in the atmosphere at very, very high resolution, like parts per billion level. So I think I've tried to demonstrate here quickly how molecules can have spectral fingerprints, and we can use artificial intelligence to identify them. I want to move forward to medical diagnosis. In medicine, there's lots of data. We have medical images, be it ultrasound, MRI, a biopsy of some cellular matter. We also have biomarkers that we measure in the bloodstream, and we also have all kinds of other patient data. There's a plethora of data, some of which fingerprints certain conditions. AI can help. Instead of having doctors exclusively look at this data and determine themselves what they believe the diagnosis is, we can at least develop AI co-pilots that can guide them along and say, hey, this is what I think, have you checked this out? So I'm gonna go through a couple examples of that, and they all revolve around women's health. And the reason we've chosen women's health is a chronically understudied area. In fact, up until the 1990s, many medical research areas had no data from women in them. And so there's lots of things that are unknown. It's a huge underappreciated, understudied field. Because of that, there's huge opportunity to develop new products and to look at diseases that previously have been unstudied. So the first I want to talk to you about today is not in fact a disease or condition, but it's in vitro fertilization, IVF. Traditional methods use hormones to determine whether or not a female can successfully undergo IVF treatment and become pregnant. So they use one of these input streams here that I've defined. We're using AI to take demographic data, hormonal data, ultrasound data, and then embryology. What does the egg look like as it's fertilized, and how does it develop within the first few days? Feeding that kind of information into AI and giving personalized predictions of the probability of successful birth. Our AI models tend to be of the order at present of 90% versus traditional means, which are about 70%. So we're able to provide some improvement. We're also looking at polycystic ovary syndrome, PCOS, which is effectively cysts forming within the ovary. And so here's an image on the left here of an input ultrasound. You see these little dark spots? Those are follicles. Follicles eventually become eggs. We use AI to treat these photos and kind of understand what's going on in all the dark space, and we're able to predict PCOS with like 98% accuracy versus traditional clinical accuracies, which could be of the order of 70 to 90. We've also looked at ovarian cancer. Ovarian cancer is a very deadly disease because it's almost always caught very late, at a late stage. The 5-year survival rate for ovarian cancer of all types is around 51%. If it's diagnosed early, that survival rate can be increased to around 92%. So that's a huge outcome if we can detect this disease earlier. There are five common histiotypes of ovarian cancer, so different types of carcinoma. What these images are biopsied cells that have been dyed in a clinic, and then they're stuck on our microscope. Typically, a pathologist will take a look at these images and determine, is that cancer, is it not, what type of cancer is it? So that's a problem where we can develop an AI co-pilot that can zoom in and identify the key features or fingerprints within these images that might indicate what type of carcinoma it is it a carcinoma at all? And our initial work on this, which is yet to be published, has shown that we can achieve accuracies of greater than 90% on these identification problems. And so AI will aid doctors in earlier and more confident, faster diagnosis and avoid some of the errors that human beings naturally create. So I hope today that you've seen two nice kind of, I call them engineering applications of AI. But if we back up to the higher level, the point I'm trying to make is that AI is a very powerful pattern or fingerprint recognition tool. We've shown these two applications in chemical detection and medical problems related to women's health, and they have prospect at least for improved environmental and human health. So thanks. I look forward to seeing any of you that stick around out here in the poster session. Thank you.